closed system and open system, right? And the test is on Tuesday, right? So I have uploaded the solution for the tutorial for you so that you can do your revision with the tutorial as well. But of course, please still come to the tutorial. Okay. Alright, so for today, for 1 hour class, we will go into second law of thermodynamics chapter. Alright, so in a way, so this is like the second half of your lecture. So usually I think of it this way lah. We have like first half is about first law, second half is about second law. So for second law chapter, you have two parts. So you can see two lecture slides in your notes, in your Google Classroom. So this will be the second law of thermodynamics. The second note is actually on entropy. You can think of it like this is more of the theory part, the other one is more of the calculation or the maths parts. So this is my... Okay, so this chapter, the basic itself is not too hard, but it can go very difficult lah. Okay, so let's look at this one. So at the start of the course, like initially we did talk about we have two different laws. One is the first law, the other one is second law. So the first law talks about conservation of energy. So we only talk about conversion of energy. So that's what you have been doing. So second law will be the law that talks about the direction of the energy, or rather we call it the quantity of the energy. Okay, so the overview here. So for this slide, we will introduce you to the second law of thermodynamics. Then we will talk about some, since again this is sort of a new thing, so just like your first half of the lecture, we will start with introducing you with some new terms basically and new phrases. So here the new terms are thermal energy reservoir, reversible and irreversible processes, heat engines, refrigerators, heat pumps. And then we will describe the Calvin-Planck and Clausius statement. So these two statements are basically the two main definition, if you want to call it, but more like the two statements that define second law. And then we will discuss concept of perpetual motion machines. We will apply second law to cycles and cycling devices. We will describe, and then Carnot cycle, some Carnot heat engines, refrigerator, heat pump, and then talk about thermal efficiencies. For today, I think mostly we will just reach Calvin-Planck statement and Clausius. That's the max. Okay, so just a repeat. First law of thermodynamics, we discussed the conservation of energy, while second law of thermodynamics, we talks about directionality of processes. So what do we mean by direction of process? So a lot of these things are more common sense to you in real life, but we rarely define them in terms of like actual value in a way when we think about it. So like I said, remember I mentioned, when you cool down something, technically speaking in engineering, we don't think of it that way because coolness, there's no such thing. We don't cool things. It's not a type of energy. It's nothing basically. We remove heat from a place because heat itself is an energy. Okay, so like this first example here, a cup of hot coffee. So energy, technically speaking, if we only look at first law, energy can go anywhere. It can go left, it can go right. So from here, in a way, if you only look at the first law, technically speaking, the coffee can take heat from a cooler room with first law. But of course, we know that heat itself is the heat energy moves or transfer through difference in temperature. It always goes from high to low temperature. So that is where we use second law. So that's where second law comes in. Okay, so same thing here. If you have a resistor wire, if you supply electricity to it, it will generate heat. But conversely, it cannot happen if you try to heat it up to generate electricity. Mostly, we do have something called thermoelectric, where we do generate electricity with heat, but the efficiency is not that high lah. And in general, actually, most of our power plant we do generate electricity with heat, but not without any work. Not without any extra effort or with very good efficiency. Alright, so same thing here also same. So same thing here. Let's say if you have a paddle wheel, if you keep turning, the air itself inside will actually get hotter. But if you try to heat up a pedal, the pedal itself won't move. Okay, so these are all what we mean by direction of energy. So these processes cannot occur even though they are not in violation of the first law. So I'm not sure if you remember, but in first chapter we mentioned that we use another two terms to define first law and second law. So first law, we say that first law determine the quantity, is about the quantity of the energy, while second law we talk about quality of the energy. So that quality is what we define as we use to determine the direction. So what do we say that? Why do we say that? So we always say that higher quality energy can go to lower quality easily, but a low quality energy cannot go to high quality energy, and it's not as easy, or not 100% in general. So just based on this statement, can someone tell me what is the lowest form of or energy with the lowest quality that you can think of? Maybe not lowest, but one of the lowest one. One of the lower quality energy. Actually, it's very obvious just from this diagram here. Heat. That's why whatever you do, you always generate heat. You use your computer generates heat. Basically, everything that you do, you generate heat, because that is one of the lowest form of quality, and that's why it's always a waste, because we don't want it, but then it keep getting converted into heat. Because heat is one of the lower quality energy, so work is a high quality energy, because that is something that we want, but you never get it. Not as much as heat lah. Okay, so the major uses of second law. The second law may be used to identify the direction of processes. It also exerts that energy has quality as well as quantity, so we just covered this. The second law of thermodynamics is also used in determining the theoretical limits for the performance of commonly used engineering systems such as heat engines and refrigerators. So this one we will look at this after a test. Basically, this is the second half of this lecture. We use second law to determine what is basically the limit of every engine. Okay, so processes occurs in a certain direction and not in the reverse direction. So in short, a process must satisfy both the first and the second law of thermodynamics before it can happen, basically. It cannot violate either one of these. So it is not just conservation of energy. Okay, so let's look at some definition now. So the first term here is called reservoir or thermal energy reservoir. So these are the body with large thermal energy capacity that can supply or absorb heat with no noticeable change in temperature. So thermal energy capacity, the equation is just mass multiplied by specific heat. In short, the thermal energy capacity is how much it is its capacity to store heat energy. So a reservoir can take in a lot of heat without any noticeable change. Of course, there will be certain amount of change, like very, very small, maybe 0.1 degree Celsius, but it's not very noticeable. So what are some of the examples of these things? A lot of these things around our surrounding. So something like this. So atmosphere, river, lake, ocean. So bodies with relatively large thermal masses. These are the things that we model as reservoir. So very logically, so something like your aircon, you have your outdoor unit, it is continuously releasing heat when they are in use, but they technically speaking don't heat up your entire atmosphere. Maybe in close proximity, if you're standing there, yeah, it is hot, but you just walk away by a certain distance, then you won't feel that heat anymore. That's what we call thermal energy reservoir. So same thing as lake, ocean, river. So these are also ideal places where we can dump heat, or in certain cases we use them to cool down whatever that we need to cool down, because once they cool them down, their temperature don't really increase as a whole lah. Of course, we are not talking about like immediately right after it. Okay, so thermal reservoir, we have two types. One we call source, the other one we call sink. So just by the name itself, source is where we take heat from. So the example that I've been giving you so far, we are examples where we try to release heat or reject heat too. Of course, then we also have the other type of reservoir where we take heat from. So something like volcano lah, that kind of things. Places where we take heat, we are taking heat from. So those are reservoir that supplies energy as heat. So in a way, sun is also one type. So that's where you get solar energy. Sink then is where we reject heat too. So reservoir that absorbs heat energy as heat. So we have two types. Okay, so we won't. So this one, I think for your syllabus, we don't. Okay, we do have such example, but here we just talk about heat engines. For now, we still don't really think about how they work yet. So a heat engine is something that generates work from heat. So work can always be converted to heat directly and completely. So we define this just now when we say that energy have quality. So work is high quality, heat is low quality. So for you to get heat is very easy. In fact, work can be converted to heat 100%. But of course, we cannot convert heat directly to work. But of course, having said that, we actually can convert. Unlike all the examples that we talked about just now, we can convert heat to work, just that not 100%. Okay, so heat engine is what we call a device that converts heat to work. So most of the power plant that we have are actually considered heat engines, but in a very large scale lah. In fact, the most direct or straightforward example, your car engine. You burn fuels, so you get heat. You convert that heat to energy. That's where you get. So a heat engine, a very simple illustration or a very general illustration, I usually will call this the second law diagram, but that's not actually the name lah. It's just something that I use it to call it. It's something that you see here in this diagram here. So like I said, a basic illustration. So you have a heat engine. So this heat engine will take heat from a source, whatever the source is. So like I say, if it is engine, then this is the petrol or the fuel that you are burning. Then this heat engine will generate work out. So we call it work net out because sometimes we will supply some work for it to start up first. Because without the work, then you cannot burn the fuel. Then without the fuel, then you cannot generate work. It's a bit of a chicken and egg issue. So you still have to supply some sort of work to it first. Okay, but like I said, heat cannot be fully generated to work. So you will get some heat loss. This is where it's very familiar. Car engine also, it gets hot. You have to reject the heat to the surrounding. Again, your computer, it will always release heat. Technically speaking, yeah, your tablet also probably some not so as noticeable as others, but you will always generate heat. Okay, so a device that converts heat to work is called heat engines. Heat engines receive heat from high temperature source. So some common example here. So here we are mainly talking about power plant. So some common example is solar engine, solar energy, oil furnace, nuclear reactor. So these are all things that convert heat. And we convert part of this heat to mechanical work, usually in the form of a rotating shaft. So in more specific term, usually these are all converted through a turbine. So you have heat, you heat up something, then that something will try to move a turbine to generate work. So it rotates the turbine. That's where we get a rotating shaft. So that's why we also always call them shaft work. And we will reject the remaining waste and heat to a low temperature sink. So somewhere else, most of the time it's atmosphere or the reverse. So this heat engine operates on a cycle. So remember what is a cycle? So cycle means that you have multiple processes, multiple states, but ultimately it will go back to the first state. So the whole thing will just move, go back to the first state, then it repeat. So in a way it will become more self-sustained because of that. So the working fluid is what we call the fluid that is working in a cycle. Basically this fluid or substance, so in what you learned with so far is water, R134A, air. So this fluid will help, basically their job is to transfer the heat to the cycle and then to generate the work and then to reject the heat. So here is a basic example of, let's say, a jet engine. Of course this is a very simplified version. The actual one won't be as simple. So a very simplified version of a jet engine will compose of 3 components, technically 5 if still there, but we don't talk about diffuser and nozzle here. So air will enter so from here, like let's say this is the engine, so air enters through here, right? The first part, the fan, actually is the diffuser. You need to slow down the air first, but we don't talk about them because they are not part of what we want here. So once it enters the diffuser, it will enter compressor. So the compressor, what does the compressor do? The compressor will actually increase the pressure of the air. Okay, and at the same time it also increases the temperature slightly lah. Then after that it goes into the fuel. It goes into the combustion chamber. So in the combustion chamber it will mix with the fuel, they will burn, then you gain heat. So here is a Q-in process. So here this is a work-in process. Like I said, you will still need some energy to start it up. So then here temperature will further increase and pressure will also, pressure actually won't. Temperature will further increase. Then this hot steam or this hot air, or exhaust will have very large energy. So this energy then will move this turbine, then that is where you get work out from here. Then we reject this to the surrounding. So this actual working you don't really need to know lah. Here this is just an example for you. So here you can see that it doesn't. Okay, so one thing that I want to ask you first, is this an open cycle or closed cycle? Okay, open system or closed system? Open system. Okay, so we actually have something that's also called cycle. So the system and cycle itself are a bit different. Later we'll see. So this one is fully open. But then but just now we said cycle always go back to the initial state, right? But then here we just release the air to the surrounding. So where does the initial state come from? Yeah, actually in a way you are rejecting this surrounding, but then you are still taking in air here. The air that you take in is always the same. So in a way it looks like it is still a full cycle because you are still taking the same air, you are rejecting the same exhaust. Okay, so this is one example where we call open system and open cycle. So you can see the name there. Open cycle because we keep changing the fluid, which is the air in this case. So this is a general case of how an engine works, a jet engine. So now we look at what we call closed cycle heat engine, which is a steam power plant. This is the most general type of power plant that we have. Closed cycle heat engine, but is this still an open system or closed system? This is still an open system, okay? So individually, because when you analyze cycle, you don't analyze cycle as a whole. You still split them into parts. So for those of you who have went through your lab, you sort of know this. Okay, so you cannot analyze this whole thing as a whole because it doesn't make sense. You still have to analyze it based on pump, boiler, turbine, condenser. So this is an example that we call this is an open system type of cycle, but it is a closed cycle because we don't change the liquid as long as there's no leakage. But in actual case, there are leakage, but in the long run, we still need to change the fluid. But in short term, we don't really do that. So this is an open system, but a closed cycle. Okay, so this one, then same thing. So you can see that overall, the system that we use don't really change much. Because right, when you look at this one, you see we have a pump. In the previous case, we have a compressor. Here is a pump because we are dealing with H2O here. Then we have a boiler, which in a way is similar to the fuel just now, just that fuel mixed with the air. In this case, we're adding heat. Then we still have a turbine that generates work. But here, we have to send the remaining hot water back to a condenser so that we can reject heat. So there's one extra step here. So we reject this heat such that it will go back to the initial state of the liquid. Then we go back to the pump, then everything repeat. So work in, Q in, work out. So this is a zoom in version of the second law diagram that I mentioned just now. So if you zoom out, this is your heat engine. So this is where your Q in come from. This is your Q out. Then this is, just now we wrote work net out, right? So it is the work out minus work in. Because the work in is usually very small. And it doesn't make sense for the work in to be bigger than the work out, then we are not generating energy anymore. Okay, so in general, this is how a power plant or heat engine works. So again, it goes the same logic as the previous one. When it goes to the pump, pressure got increased so that we can send it to the boiler. Then the boiler will add heat to the system. Then the hot steam. So in this case, easier to imagine. Water, basically whenever you add heat or energy to the fluid, the molecules get more excited. So you got more energy. So in this case, you can easier to imagine because your liquid water will get changed into a superheated vapor. So from liquid to vapor, then this vapor will push the turbine and in turn it generate work. Then it goes back to the condenser, we condense it back to a liquid. Then the process keep repeating. That's how we generate energy. Okay, so here, this term here, then here this will be your heat source, this will be your sink. Okay, let's look at this further. Essentially, this was what I talked about just now as well. So a portion of the work output of a heat engine is consumed internally to maintain continuous operation. So of course, initially when we started this whole thing, you still need some form of work to make this work first. But after that, then the work in here actually comes from the turbine, which is why usually we just define this whole thing as work net out. Okay, so for this kind of heat engine, so like I mentioned, we know that heat cannot be 100% converted into work. As you can see here also, we will have some Q out. So we need to define the efficiency of this kind of heat engine. So what we use is the term we call thermal efficiency. So thermal efficiency, how efficient is the thermal energy? So thermal efficiency. Of course, the definition, the way efficiency works, the equation is still very standard. Desired output over the required input. So the input here is heat input, but the desired output here, just brief first. But the desired output cannot be simply work out because you are using certain amount of work in. So you still have some input there. So that's why we call it the net work output instead of just work output. So the net work output is work out over work in. So in a cycle, if we assume that there are no losses, right? So in the cycle, let's say if we assume that there is no cycle, energy in should equals to energy out. So the energy in here will be work in plus Q in actually, then Q out plus work out. And logically speaking, we know lah, Q in should be higher than Q out, work out should be higher than work in. That's why we end up with Q in net equals to work out, work net out, whichever one comes first lah, doesn't matter. And this is the whole basis. So remember in closed system, the equation, I said that the general form is Q minus out. because this is what we are expecting. So basically, in general, we are expecting we are throwing in Q in, we are getting work out. That's why the general equation in the closed system is Q minus W. That's all. That's the whole reason behind it. And when you expand, you still get work out minus work in minus Q out, right? So it's the same thing as this actually. So here, we know that work net out is equals to Q net in. So if we expand, then Q out, and then this Q net out is actually Q in minus Q out. And we also call this QH minus QL. But this one, right? Okay, I'll just put it out here. For some reason, they like to use system. I don't like, but I still have to teach you because that's how we use the term. Why do I say I don't like it? Because QH essentially means the heat energy transfer from the high temperature side, which is the high temperature reservoir, as you can see here. QL is the heat transfer at the low temperature reservoir, which is here. So that is the only meaning. So you can see the definition at the bottom as well. It says heat transfer between the device and high temperature reservoir, and QL is heat transfer between the cyclic energy and low temperature reservoir. That is all. QH doesn't mean Q in, and Q out doesn't mean QL. Again, if you have went through your lab, you will realize this if you compare. In lab, this term will swap. So you don't memorize it this way. So like let's say in an exam, if you decide to write Q in and Q out, I'm fine with it. But your equation probably will be given in terms of L and H. So be careful a bit about that. But I'm okay with either lah. They are interchangeable to me because the meaning is the same. Okay, so let's say in this case we say Q in is QH, QL is Q out. So then we can change this thermal efficiency equation to QH first. So then we replace work net with QH minus QL. Then we get a new equation in terms of just QH and QL, or Q out over Q in. So 1 minus Q over QH or 1 minus Q out over Q in. So thermal efficiency equation, you have two forms. But in general, again, like I said, I don't recommend, I cannot remember whether I give you the second form of this equation. But in general, yeah, this is a very easy to derive equation. So I don't recommend you memorizing anything lah. Just keep to this one. Then if you can remember this one, then you can solve this whole thing. So meaning, if you can remember work net is Q in minus Q out, then just use the normal thermal efficiency equation. Okay, so thermal efficiency equation, yeah, we just derived this. So some heat engines perform better than others because where they can convert more of the heat they receive to work. But even the most efficient heat engines rejects almost 1/2 of the energy they receive as waste heat. So yeah, that's pretty much what I want to tell you lah. The meaning, like we said just now, heat cannot be converted efficiently to work. So most of the time we have a lot of waste heat. Okay, so can we save Q out? So what we are trying to say here is this. In a steam power plant, the condenser is a device where large quantities of waste heat is rejected to reverse lakes or atmosphere. Can we just take the condenser out of the plant and save all the waste energy? Meaning, what we see. Okay. Not in the diagram, but anyway. The answer is no, obviously. Without heat rejection, this process cannot happen. So why is that the case? Because we want this whole thing to work in a cycle. So look at the diagram here. Initially, let's say you have a gas of So look at the diagram here. We initially have a gas of 30 degrees Celsius. We heat this up. So here this one is just a closed system example. You see, and it has a load on top of it. The load itself, you can imagine it as the work out. Okay, so you are heating the gas up to 90 degrees Celsius. Then during this process, the heat that you supply to it managed to move this load. Let's say the work required to move this load is 15 kilojoule. So yeah, so when you provide heat, it managed to do this certain amount of work. So it is generating a certain amount of work. But let's say if you don't cool down this process, meaning you don't reject the heat that the gas has gained, this process cannot continue because it will just keep getting hotter and hotter and hotter. Then it doesn't make sense anymore. So you can't, it's not sustainable anymore. So for a one-time thing, it makes sense. But the energy will still remain in this gas. So this gas will still have a very high temperature in this sense. So you cannot reuse this gas anymore. So that is why we reject heat. We reject heat. But when you reject it, so this is the amount. So you can see if we supply this amount, you only get this much work and you need to reject this much for it to go back to initial state so that it can redo the same amount of work again. So this is why we have a cycle for energy generation. And this is why we have to reject heat to the surrounding. So every heat engine must waste some energy by transferring it to a low temperature reservoir in order to complete the cycle. So even under the most idealized condition, so let's say we say no losses, because we don't consider heat rejection as losses because we intentionally reject this heat. Okay, so here we have one example. So this is a very simple example. Net power out production of a heat engine, we are just calculating that. So heat is transferred to a heat engine from a furnace at a rate of 80 megawatt. If the rate of waste heat rejection to a nearby river is 50 megawatt, determine the net power output and the thermal efficiency. So here very straightforward, you are given QH or Q in, you are given QL or Q out. Work net is simply their difference. And for thermal efficiency, yeah, so you can see here, this is what I meant. So for thermal efficiency, we just use back the original equation, which is work net over QH or Q in. Of course, you are not wrong if in this case you want to use the equation Q1 minus QL over QH is equally applicable. It's the same thing. Alright, then here it does show you that the efficiency is not very high here. So this efficiency means that only 37.5% of the QH is converted to work net. Okay, so here we have another example, so another simple example here. So far our calculation will be pretty straightforward because like I mentioned, this slide itself is more theory. The next slide then will be more maths. Okay, so a car engine with a power output of 65 horsepower. So horsepower is one of the things where you are not expected to know the conversion. Okay, if it comes out in exam, I will give you the conversion. So it has a thermal efficiency of 24%. Determine the fuel consumption rate of this car if the fuel has a heating value of 44,000 kJ per kg. So heating value of a fuel is essentially how much heat it will release when you burn it. So that's the definition there. That is 44,000 kJ of energy is released for each kg of fuel burned. Okay, so maybe since we are here, then maybe I talk a bit about this also. So sometimes in exam, right, actually you will see some example like this also in maybe if you do some past year, but I can't remember when, maybe long time ago, maybe recently. But sometimes you will see that I do give you something like this where you might not understand what the term means. So I will put a bracket there and I say, so you have to know, you need to understand what I'm trying to explain here. Okay, so because sometimes it's just some additional thing like this. So like in this case, we know the thermal efficiency of the engine. We know the power output of the engine. So the conversion is here. Okay, this is the conversion. So 1 horsepower is equal to 0.7457 watts. So then based on these two things, you know that we can find out what is Q in, right? So that is 202 kilowatts. And then, so how do we find the fuel consumption of this car? So we know that this is how much heat that we need to supply. Then it actually becomes very simple because it will simply be QH equals to m dot. What's heating value? If I remember correctly, heating value is something like this. This is a variable for it. So, but anyway, so this will be the heating value. So m dot multiplied by the heating value or you can think about it as enthalpy also. So then, yeah, so the fuel consumption is the mass flow rate of the fuel, right? So then you can get it just from the QH and heating value. So from here you can obtain what is the fuel consumption of the fuel. So how much fuel you need in order to generate this much power for the engine. So note that if the thermal efficiency of the car could be doubled, the rate of fuel consumption would be reduced by half. Logical, right? So this is what most engineers will try to strive for when you are designing all this thing. We want a better conversion of energy so that you can save more fuel or produce more power depending on which one is your aim. Okay, what time is it now? Okay, then we talk a bit about Kelvin Planck, then we are done for today. Alright, so just now I mentioned second law, we have two statements that define second law. So the very first statement, actually these two statements are very logical. This first statement, we just talk about it. So you can see the law definition here. It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. What we are saying here is this is not possible. So from here, you cannot, basically we are saying that there is no heat engine that has 100% efficiency. Okay, so you cannot receive 100 kilowatt and generate 100 kilowatt without without rejecting any heat. So this is what a Kelvin Planck statement is about. So no heat engine can have a thermal efficiency of 100%, or for a power plant to operate, the working fluid must exchange heat with the environment as well as the furnace. So the environment part here, we are talking about this one lah. While furnace, we are talking about this. Okay, so that is the limitation of this case. Basically, you cannot completely convert heat to work. And when we are saying that not completely heat to work, we are not talking about, like, let's say friction or other losses. Losses, we talk about them later. Here we are just purely talking about energy conversion without losses. So we are saying that this is not possible. Okay, so one example here, actually is similar type of example lah. A 600 megawatt steam power plant, which is cooled by a nearby river, has a thermal efficiency of 40%. The spelling is off. Determine the rate of heat transfer to the river water. Will the actual heat transfer be higher or lower than this value? Why? So when we talk about 600, okay, so when we talk about a power plant with this kind of power rating, let's say 600 megawatt, once again, we are always talking about network. It's not work out. It's always about network. So if we say something have this power output, again, it's always about the network lah, unless it specifically say that we are talking about the work output from the turbine. Otherwise, it's always the net. Okay, so for this case, okay, so far, all the previous example, we didn't talk about this, but yeah, always remember this one. We have assumptions. So power plant, just now I showed you power plant, we have all open system inside it, right? So so you can see we still have this assumption here, steady operation, so operate steadily. Then here in this case, we are neglecting all the heat losses to the surrounding. So based on this question, we can once again we can use the work output and the thermal efficiency to calculate the QH or Q in. So the rate of heat transfer to the river, then based on this, we can just use the other way around, meaning, we can just use the work net minus work QH minus work net in order to get the heat rejection to the river or surrounding. In this case, it's river water. So 1005 is the heat you supply, 600 is what you get, 900 is how much you reject. So in reality, the amount of heat rejected to the river will be lower, since part of the heat will be lost to the surrounding air. So like in reality, let's say you probably will think that this amount will be lower as well. Then maybe we will reject more heat. But of course, the reason why this amount is lower is also due to all the losses. So friction loss in the pipe, heat loss to the surrounding. Then after that, when you reach the condenser, same thing. we have all those losses. So in reality, everything will be lower. So this QH will be low, QL will be lower as well, since part of the heat will be lost to the surrounding air from the working fluid as it passes through the pipes and other components. Okay, next slide we are entering new thing already. So this is about the next statement. So I think I will stop here or else I don't have time to finish this. Alright, so reminder, Tuesday is your test, don't come late. Alright. Then yeah, and again I have uploaded the solution for the next tutorial so you can use it for your revision.